Okay, today we're going to look at derivatives of logarithmic functions. Before we start those derivatives, we need to look at some of the properties of exponents and logarithms because they will aid us in determining the differentiation rules for logarithms. Okay, one's converting between logarithms and exponents, and the other is the change of base formula. So first off, remember a logarithm has a base, there's a number, and there's a value to the logarithm. So log of 64 base 4 is equal to 3. The related exponential function with this would be to rewrite this as 4 to the third power equals 64. So every logarithmic function can be rewritten as an exponential function. The other thing is if we're doing logarithms, sometimes we don't quite have a value. The log of 17 base 4 is saying 4 to what power will give us 17? Well, it's bigger than 2 and it's smaller than 3, and probably closer to 2 since 4 to the second is 16. And we don't have a base 4 logarithm key on our calculator. But we do have common log keys and natural log keys, so we're going to use those ideas to help us express this. We have the change of base formula. So here we're going to change the base from base 4 to base e, the natural log. So the log of 17 base 4 can be written as the natural log of 17 over the natural log of 4. And then we could simply plug those into our calculator and evaluate. Now we're going to use these to help us find logarithms. So here we're going to begin with y equals the natural log of x and calculate its derivative, just like we began with y equals e to the x and did its derivative first. So y equals natural log x. My base is e. And like I said up here, I can take any logarithm and change it to an exponential function. So here, since my base is e, I could rewrite that as e to the y equals x. And now we can differentiate both sides. So if we take the derivative of e to the y and the derivative of x, let's see, the derivative of e to a power is e to that power. So it's going to be e to the y times the derivative of the exponent. The derivative of y is 1 dy dx. So some implicit differentiation comes in here. And the derivative of x on this side, that derivative is 1. So dy dx is equal to 1 over e to the y. Up here, we know that e to the y is equal to x. So our derivative turns out to be 1 over x. So we can summarize that now to say that the derivative, if we differentiate natural log of x, that's going to become 1 over x. Now, if we're taking the natural log of a function of x, then the chain rule can be applied. So if we're going to differentiate d dx, the natural log of u, where again u is a function of x, the derivative is going to be 1 over u times the derivative of that u, or simply u prime over u. So for this problem here, which is obviously split from the text, to calculate the derivative here, dy dx is going to equal, this is my u, so it's going to be 1 over u, so the x squared plus 5x minus 12 is my u, so it's takes the place in the denominator. And my numerator is the derivative of u. So my numerator is going to be 2x plus 5. And that would be our answer. Sometimes we may be able to factor the denominator and it cancels with part of the numerator, but the numerator is 2x plus 5, and there's no way we're going to get a coefficient of 2 in the denominator. If we move on to general logarithms where the base is some number, a, like a base of 5, a base of 4, a base of 8, a base of 12, they're all going to work the same way. Let's see, over here, let's see, we have the log base a of x. Well, there's no base a logarithm key on our calculator, so we're going to change the base. We're going to rewrite this as the natural log of x over the natural log of a. Okay. And that's actually equal to 1 over the natural log of a multiplied by the natural log of x. If we were dividing by 2, it's the same thing as multiplying by 1/2. We're dividing by natural log of a, so it's going to be 1 over natural log a. Remember, a is a numerical value, so natural log of a is also numerical. So if we look at this, it's going to help us find our derivative. dy dx, well, the derivative is going to be the constant multiplied by the derivative of the function. Well, the derivative of natural log of x is 1 over x. Or in this case, 1 over x natural log a. And then again, if we're talking about a situation of where we're taking the logarithm of a function where the chain rule can be applied, here we'd be doing d dx of the common log of a of u, where u is going to be a function of x. This is equivalent to taking the derivative of the natural log of u over the natural log of a. And as we saw before, that's going to be 1 over the natural log of a. And then the derivative of natural log u is 1 over u. And then we're going to have to multiply by the derivative of u. So overall, we simplify this and pull pieces together. We've got u prime over u natural log a. So on this last example, y equals the common log, the base 3 log of x cubed minus 5x squared plus x minus 7. That's the u. In this case, u prime would be 3x squared minus 10x plus 1. And so our derivative in this problem, dy dx, make sure you're always identifying what you're writing. We're writing the derivative, so write dy dx. A is equal to u prime, 3x squared minus 10x plus 1 over u, x cubed minus 5x squared plus x minus 7. And that's times the natural log of the a, which in our case here is 3. And that would be the derivative for this problem.